Hey everyone. So, here in chapter 30, we are getting into the world of magnetodynamics, which is where the magnetic field or magnetic flux is changing in time, right? Chapters 28 and 29 only dealt with static or constant currents that produce static or constant magnetic fields, okay? So what I have here in this diagram is a straight wire with some current, right, externally applied, so connected to some battery shown out of frame. And beside it is a conducting loop with a resistor in there. You can think of as a real life example a light bulb, right? Same thing. And we're taking this loop and moving it to the right, so away from the wire, right? At some, say, constant velocity. There's a magnetic field around this wire, right? And because the current is going up, that means on the left side, the magnetic field is coming out of the page, and on the right side, it's going into the page. So I'm going to try and draw it such that the field line density is higher, closer to the wire, because the further away you get, the weaker the magnetic field. Something like that, although that kind of looks even, the last one. There. Okay, so the further away that this conducting loop gets from this wire, the weaker the magnetic field, and more importantly, the weaker the magnetic flux. Whoops, I want that in black. So what's called phi, the Greek letter phi, right? And some books, or you may see it have these, it's like a capital I with a circle in the middle. I find it's just quicker, and a shorthand is to just do the one vertical line and the circle. Either's fine. So that's the magnetic flux, right? And that's the closed integral of B dot dA. So we have that in this case. The flux is simply the area inside that conducting loop, and the magnetic field is the field generated by the current in this long straight wire, right, B. So that the conducting loop, the area is moving through some field, and thus there is some magnetic flux. What Faraday's law is, which is the first and, well, the next major law in 4B, is that it says that if the flux is changing, if the magnetic flux changes in time, there is a current induced in a closed loop. And so if this is how we write the magnetic flux, if it's changing, oops, yeah, changing, we have d dt phi b, and that means that that closed integral is changing. Okay? So this entire closed integral can change in time. If it does change in time, there arises an induced current in this closed loop. So either going this direction or that direction. Okay? We'll get to that in the next video. But this is Faraday's law, and this is known as the EMF, or the electromotive force. And it's kind of a misnomer in that this is not a real force. This is not an actual force. It's just was called this historically, and the name has kind of stuck, right? It's given the variable or character this kind of script E, script capital E. That's known as the EMF. And this is when the magnetic flux is changing in time. That is the EMF. And what it is, well, it basically means that the charges in this wire, in this current loop, right, that constitute this wire, there's some quote unquote force that's electrically moving them around, right? And that comes from the fact that the magnetic flux through this closed area that that wire encompasses is changing, either increasing or decreasing. Right? And that's why we have, well, it's moving, it's being pulled away at some speed. So you might say that the flux in this case is decreasing. Okay? If it's moving towards the wire, the flux would be increasing. Right? So now, what part of the magnetic flux, or rather I should just do, what part of the magnetic flux integral is changing in the case shown above? Is it the value or magnitude for the magnetic field? Is it the area that's changing? Or is it the angle in between the two that's changing? Right? It turns out that it's actually the value for the magnetic field. Right? So B can change, the area can change, or the angle in between B and A can change. In this case, so here or above, that might be a better one. Above, B is changing. And it's changing because it's decreasing in magnitude as it gets further away. And so there will be an induced current around this loop either that way or that way. The next video we'll see, which is on Lenz's law, that will tell us the direction. Okay, so this is Faraday's law. The EMF is equal to the change in magnetic flux. Right there.